Okay, we're going to be working on the paper chromatography lab. And so when we start with this, the background information for this lab, I'll start right here. The word chromatography, let me select draw here. The word chromatography literally means writing with color. In paper chromatography, what we're going to be doing here is essentially looking at your solute, we were told right here, and partitioning the solute between the mobile phase and stationary phase. So I'm trying to go over the critical information that pertains to your lab, but please be aware paper chromatography is only one of several chromatographic techniques that include the column chromatography, gas chromatography, and liquid chromatography, okay? So we are working with the paper chromatography. Let me make sure I'm actually recording here. Okay, great. So we're told here in this process, the way this works is a solute is partitioned between a mobile phase and a stationary phase and travels a distance from an initial sample spot. Okay, what does this mean? Your solute here, solute, will be the food color. So I'm gonna write here, it's gonna be food color. And this food color will be partitioned between a mobile phase that will be the solvent that you put the solute, you put the paper in, and a stationary phase. The stationary phase here will be the paper. So let me write what the mobile phase is. Mobile phase. The first one is going to be, I think, is isopropyl alcohol. So this would be your alcohol. That's the liquid that you place the paper in. And then the stationary phase, this is going to be your paper. Stationary phase, okay? So to kind of go off script, to give you the bottom line. Oops, sorry, what am I writing? This is what happens when I'm trying to talk and write at the same time. This is going to be your paper right here. Back to writing. Paper. So you copy your paper, okay? So the solute is drawn to one of these more than the other, okay? So it's being partitioned between these two phases here. The mobile phase, the phase that actually moves, which is the alcohol. The stationary phase, the phase that doesn't move, that's the paper. Okay, so I'm right down here. And remember, the solute, the food color, will have to travel a distance from the initial spot, okay? The stationary phase is either a solid material or a coating that covers a finely divided solid. In our case, the stationary phase is your paper, okay? The components of the sample spot are eluted by the mobile phase. So the components they're referring to here is your food coloring may be made up of more than one color. In that case, the different colors that come together to make your food coloring, that'll be the components, are separated. Eluted means separated by the moving mobile phase, okay? So I have a picture here that somewhat describes what's going on. Not the best, but it sort of describes what's going on. And here, let me see. I had to figure out how to scroll down here. Okay, so looking at this right here, I have tried to outline what your experiment might look like. Okay, so once again, going off script, the copier paper is the stationary phase. This is the phase that's not moving. And then down here, we are told that the copier is the least polar component, is less polar, okay? Your solute, the food coloring, has its own polarity. The paper has its own polarity. And then finally, the alcohol has its own polarity. So when you're comparing these three here, just to kind of make a point, I'm going to assign numbers to this, okay? To make it a little bit more clear, a little bit more crisp. Let's say the polarity of the paper, which is least, right? Least polar. let's make this polarity value of 1. So let's say the polarity here, the value is 1. And then the polarity of alcohol, I'll say alcohol has a polarity of, let's say, 5. Okay. And then let's say that you have a food color that has a polarity of, let's say, 4. If your food coloring or the food color has a polarity that's a lot closer to the mobile phase, it tends to move with the mobile phase. It tends to be drawn more to this mobile phase here because their polarities are more similar. 4 is a lot closer to 5 than it is to 1. Okay, so there's a competition for the attraction there's a competition between the mobile phase and the stationary phase for the food color. Okay, so once again, me going off script, when you do apply your food color to the paper, the food coloring will bind first to the paper. The food color will bind first to the paper, right? And so here in this hypothetical example I provided, you have 6 different food colors. Sadly, they all look the same, right? But imagine them being different colors, right? Color 1, 2, 3, 4, 5, 6. When you're actually applying the colors, please make sure you're following the directions in the experiment. You want to make sure the spots are tiny. And when you're applying, because they'll ask you to apply more than one spot to the same, like for color 1, you apply many, you have many different applications here. I don't know how to say that. You won't just apply one dot. You make sure you add enough of the color in here so that when you're separating the color, you're actually able to, the separation will be visible, okay? I'm struggling with the words tonight. Anyway, make sure in between additions, you allow the color to dry. If the color dries well between additions, you will have a tiny spot, okay? So we want a tiny spot here. We want the spot to be darkly colored so that when we're separating, we can actually easily trace where the color is going, okay? So you want a tiny spot. Make sure you allow the color to dry between applications, okay? As it will say in your directions, you're gonna mark the starting point. So I look at this kind of like the beginning of a race, okay? So this is like on your mark level. This is where the blocks are. Is that what they call them, the blocks? Right. So you have this color right here, this color right here, and we have 6 different colors. So in the beginning, the colors are given a chance to bind with the paper or to adhere with the paper. So the colors are drawn to the paper, okay? And then remember, this piece of paper is then one end, this end here, is attached to that end to make kind of like a column, right? After you've applied all the colors, you want to make sure if this is red, you want to, write here, this is red. If this is blue, you want to write here. I guess I can change the color here. Oh, I can do that. Okay. If this is blue, you want to write that this is blue. Let's say this is green. I'm trying to make a point here. You want to write this as green, right? That way you know the original color you placed on the paper. Once again, follow the directions. I'm kind of going off script here. Once you allow these to dry, you're going to make sure that you mark the level where you put these dots. You want to mark the starting point so we can figure out how far out these spots are going to move, right? These colors you've placed here. Okay. Then, of course, you're going to be placing this rolled up piece of paper with your color spots in a beaker. And the beaker will be, it won't be filled, but it will have your mobile phase in there. So once again, I'm going off script, mobile phase. So your mobile phase is in here. Let's pretend the level is here. And then you have your piece of paper in here. So I'm going to draw the paper with the color, let's say light blue. Maybe I should go darker. Hold on. Let me undo this. Go with, black piece of paper. Oh, the outline, okay, right there. And the paper is also rolled up, right? The paper is rolled up here. So excuse my horrible drawing. And then you want to have your different colors one right here. The colors have to be above the liquid. They cannot really be in the liquid because you don't want them to just dissolve into the liquid. You want them to be above the liquid. So of course, the directions will tell you all that stuff here. So imagine these spots are here. I'm going to try to use different colors to illustrate that part here. And then let me get a blue. Gotta have a blue. Okay. So back to where we were. I kind of, really got off script here. In the first part of the experiment, your mobile phase is the alcohol, isopropyl alcohol. Okay. As the alcohol begins to travel up the paper, depending on the polarity of the colors, remember the alcohol is more polar. So comparing these two, the alcohol is more polar than the paper. Okay. So let's say the color yellow is more polar and the alcohol is traveling up here and the alcohol travels to this level right here. So this is the level traveled by your mobile phase, the alcohol. If yellow is more polar, then we expect that this yellow will actually travel with the alcohol. So sometimes it leaves a trail, but it travels up here. Okay, so you won't see it down here anymore. Now the yellow will be up here. So how do I erase this? Oh no. Okay, I erased more than I meant to erase. This is a struggle, y'all. Okay, there. Now we see that the yellow has followed the mobile phase because it has a preference for the mobile phase over the paper. Remember, each of these colors is either being drawn to the paper more, and if it does so, it is less polar, or it's drawn to the mobile phase, the alcohol. If it's drawn to the alcohol more, it is more polar. It tends to go after the chemical that it's more similar to, okay? And the factor that separates the colors is the polarity of the mobile phase, okay? So once again, the mobile phase is more polar. That being the case, so right here, I need to make sure I write this down. More, I need to use blue. It's a struggle, y'all. More polar, okay? And because the mobile phase is more polar, that means by default, yellow is a polar dye, okay? And it's more polar than the other ones because it traveled the most. So let's say for the sake of the discussion, red traveled also, but not as much. Let's say, how do I get this to work? Click. Okay, hold on. Click here. Why is this not changing? Click down here, click here. I think I broke this. Oh, because I still have eraser selected. Oh my goodness. Okay. So I need to go back here, click red. There it is. So, sorry. Now back here. Say the red traveled, right? The red dye traveled only this far. Then we can say this is also polar, but it's less polar than the yellow dye. Okay. And then let's say that the blue didn't travel at all. If the blue didn't travel at all, but the green traveled a little, then let me go back here and erase this. Go back here. I have to remember every click. Okay, so let's say the green is right here. Then we can conclude that the blue is the least polar. Okay, least polar. Once again, this is just for illustration. Why can we conclude the blue is the least polar? The blue prefers to be with the paper, and the paper is also has a lower polarity, right? Of the three components, the paper is the least polar component. Okay, like dissolves like. Okay, so once we figure out that the moving solvent will not only pull out the dyes, if you had a mixture, if you had a dye that was made of a mixture, let's say, for example, this is blue, and instead of having blue here, say we had pink. Oh, no. Let's go with orange. Say we had orange, okay? I have to add this somewhere in here. So say we had an orange dye, and the orange dye was here originally, right? And orange, I would say orange is made up of yellow and red, right? So say we had orange originally, and then of course we put the paper in the solvent. The solvent has already moved, and this is what is called the solvent front right here. What do we expect to happen with orange? Since orange is made up of a mixture of two different dyes, the yellow and the red, right? What we expect to see after this orange has moved is you won't see the orange color anymore or the orange dye. What you will see is, hold on a second, you will see a faint red that will be similar in position to this red here. And then you will see a faint yellow that will be similar to this position here. But you know that this, when it traces back to the starting point where you marked, right? You know that this came from the orange. So this tells you that these came from the orange, and the orange is made up of two colors. And these colors are red and yellow, okay? So chromatography can be used to separate colors into the components. So when you go through here, it tells you all that stuff, okay? Once again, whenever we're done with all of this, you're gonna be figuring out the retention factor. So the retention factor helps us to determine of the dyes that we have, which is the most polar, which is the least polar, which traveled the most, and which traveled the least, okay? So imagine this piece of paper up here. Hold on a second. This is the paper before you put the paper. This is what the paper looks like, right? Before you put it in the beaker. And this is the paper after you put it in the beaker. So we want to make sure we know what these levels are right here. As I mentioned before, I try to shade this area and make it look blue so that you can recognize that this area here, let me change the color before. Yeah, this is called the solvent front. So this is how far, this is where the solvent traveled to, right? When you put the piece of paper in the water, the solvent traveled this far. So it's called a solvent front, okay? The mobile phase traveled this far. Okay, so remember the mobile phase, this here is relatively more polar. So we got more and we got polar right here. And of course, the paper is the least polar. So looking at this right here, when you want to figure out the RF value, I need to have numbers. So let me go ahead and assign numbers just for the sake of it. Let's say this mobile phase has traveled 10 centimeters, okay? I'm just giving it a made up number. And let's say this one here has traveled 8 centimeters. Then I have 7 centimeters. Then here I have 6.3 centimeters. Here is 6.5 centimeters. This one didn't travel at all, 0 centimeters. Here I have, 6.3. Here I have, let's say 2 centimeters and 2 centimeters. These look right about even, okay? So based on this, I will figure out the RF for each of these colors, right? And the RF is the retention factor. So going back here to this part here, since I've gone off script. Oh, I'm in a whole different lab. Where is this? Right here. The retention factor, let me go ahead and erase this so it's out of the way. You're figuring out the distance traveled by the solvent, or in this case, the distance traveled by the color divided by the distance traveled by the solvent. So they've pretty much shown you what is what in this picture right here. See, they have their own picture and I have my own picture. This one here is colored, mine is not, okay? So distance traveled by solvent is L solve, that's the part here. Distance traveled by color. And if you have a huge spot, try to get the distance from the starting point right to the middle of that huge spot versus the top of it, okay? So right in the middle of that huge spot. If it's kind of smeared, you want to get to the middle of it. Hopefully that makes sense, okay? So I provided numbers here to make sense of this. Let's see what we can get for our RF values. For this color number 1, my RF value for this RF equals 6.5. This distance traveled here divided by the distance of the solvent. The distance traveled by the solvent, that will be divided by 10. This is centimeters, horrible handwriting. My RF here is what? 0.65, okay? So I have to go through and divide all of these by 10. So imagine I'm doing that, right? This is 7 divided by 10. The RF here is 0.7. And then here, the RF 2 divided by 10. Divide each of these by 10, right? RF here is going to be what? 0.2. 0 divided by 10. The RF for this is going to be 0. This one here is 2 divided by 10. The RF is 0.2. Here, the RF is going to be, once again, 8 divided by 10 would be what? 0.8. And then the RF here is going to be 6.3 divided by 10. RF is going to be 0.63, okay? So like I showed before, the most polar dye is color number 5. Color number 5, based on this picture I have here, is only made up of one component, right? So we have 1, 2, 3, 4, 5, 6. Look at color number 6. Color number 6, even though you can't tell right here because they all look the same, is made up of a mixture. It's pretty much a mixture of 2 different colors. What colors are those? Look at the RF. The RF here matches with that, and this RF here matches with that, right? So that being the case, color number 6 is a mixture of 2 different colors, color number 2 and color number 1, okay? Anyway, so I explain right here. Let me see what I wrote. It's been a while since I wrote this right here, but color 5 traveled the furthest and it's most attracted to the mobile phase. This will be reflected in its RF value, right? This will have the highest RF value because it traveled the most. Color number 4 traveled the least distance. It is most attracted to the stationary phase. This will be reflected in the RF value. The RF value is the least, correct? Color 6 separated into 2 components, as you can see right here. Color 6 is a mixture of color 1 and color 2. So yeah, I'll let you figure out the remaining relationship with the colors. Okay, so essentially this handout I already have posted should help you, make sense of this. So in your experiment, of course, it's telling you what to use. You're going to be using a beaker. That's essentially the beaker I drew up here. I've already erased it. The pencil is where you're going to be marking the spots before you put on the color, or before you spot the colors on there. The white copy paper, that's what's going to be used as the stationary phase. You have the colors red, blue, yellow, and green. And then let me see. Your first solvent is going to be rubbing alcohol. We're told that rubbing alcohol is relatively low polarity. That's isopropyl alcohol. This is all relative. So it's lower in polarity compared to the one that has the mixture of water and alcohol, okay? So we expect to see a separation here, but not as much as the one here. Technically, the color should separate more here because the separation between, the difference in the polarity between the mobile phase and the stationary phase will be much bigger. So you should see bigger values, right? Larger RF values, because the colors will travel more. Okay. But yeah, this is the gist of the lab. So the rest of it is essentially you just recording the RF values for each color dye right here. answering the following questions. I pretty much help you answer these questions in the indirect approach, or should I say, not really indirect, but in the example I provided, right? So after you watch this video, if you still have any more questions, please let me know, okay? I am done for the day, so I'm gonna wrap this up right here. Okay, once again, if you have any questions, please send an email, okay? Thank you very much.